So welcome everybody. Are you waked up? Really? Eh? Are you here? Yeah? Show me that you are here. Everybody is here. That's great. So welcome again on the second day of our conference. I have two organizational announcements. The first one that we will have the discussion panel in the afternoon today, and another is the banquet tonight. And please keep your badges, your name tags for the banquet, because it is your entry ticket. So that's your ticket for the banquet. So please keep it and bring it to the banquet. There will be some buses that will hold you to the banquet, and they will start at 7, either from here, in front of this building, or there will be the other buses at the Monopole Hotel. So if you are not far away from Monopole Hotel, so you can just walk or arrive, come to the Monopole Hotel and get on the bus to the banquet. Okay, so I suppose that we can start. We will start with very strong accent tonight, in this morning, namely Jiawei Han. He is a great computer scientist and Abel Bliss professor. It's a chair professor, which is not so well known for us, being the chair professor in the Department of Computer Science at the University of Illinois at Urbana-Champaign. And previously he was in Canada at Simon Fraser University. He's also the director of Information Network Academic Research Center, supported by US Army Research Labs. His research in general focuses on data mining, data warehousing, database systems, including knowledge extraction from spatial-temporal data, web data, as well as social and information network data. So this information networks is the leitmotif of his research quite recently. Jiawei has published several books and over 500 peer-reviewed papers, which received over 100,000 of citations in Google Scholar, which is great, especially for computer scientists. So he is a great man. He has also chaired or served on program committees of over 100 international conferences and various workshops. Jiawei is also an ACM fellow and IEEE fellow. He received an ACM SIJKDD Innovation Award and the IEEE Computer Society Technical Achievement Award. He was the winner of the McDowell Award, which is the highest technical award made by IEEE. His book on data mining concept and techniques is a very popular textbook worldwide used at many universities. Besides, since I met him at one of the conferences several years ago, somewhere in Asia, I have always seen Jiawei as a very cheerful and friendly man. So that's a great person. So he will provide us the data mining perspective, which is important also for this edition of the NetsciX conference. So this perspective for complex networks, in particular for heterogeneous networks, extracted from massive textual data sets. So ladies and gentlemen, Jiawei Han, here you are.
Thanks a lot. Good morning, everyone. Thanks a lot for Professor Sherman. Give a very nice introduction. I'm honored to speak in this forum. Actually, last year for the NetsciX 2015 in Rio, in Brazil, I also give a keynote speech. But this one could be a little different. Even you were there, you probably find that there are lots of new things, because of many things that happened in this talk actually happened in 2015. It's just within a year. So my point, I probably use the other phone. Okay, so I hope you still can hear me. My point in this talk essentially is trying to argue we see networks, lots of networks, like computer networks, web, social networks, but we may or may not realize actually we are soaked with networks even you may not explicitly link them. So what my argument is, network actually is everywhere to do prediction. Okay? For example, we try to predict co-authors, like who will be a co-author in the next several years. Okay? New co-author. Okay? Actually, this one was triggered by Christos Valoutas. Once I was in Barcelona to give a keynote. Okay? I give the previous slides. Christos was very excited. He raised a question. He says, Jiawei, can you predict next year what papers I'm going to write? Okay, which is a tough question. Frankly, I say, I do not even know myself what paper I'm going to write in next year. How can I predict you? Okay. I brought that question back to my student, Sen. She was serious. She says, of course I cannot predict the exact title because, he can change his title in the last minute. Okay. But I can predict, what topics he's working on, which is not hard at all. Okay. So she said, I can give myself an even tougher time, say, predict what will be the co-authors, for Christos in the next several years. Okay. I said, that probably is not possible because you do not even know what new student you will get. How could you predict? She says, I do not intend to predict anything not in the database. I just, based on the current database, I try to predict who were likely to be his co-authors. Okay. Then we look at the problem. The problem, actually, if you want to do prediction on the co-authors, okay. A lot of people are thinking this is a linked prediction just based on authors and co-authors. Okay. Actually, if you sit back and think you are going to have this one as your co-author just because you have an author and this author co-author with the other author, you use co-author relationship only? Actually, it's not. If you think about why you want you two become co-authors, very likely you are working on the same topics. You publish in a similar venues or something. So it's heterogeneous information that will play an essential role. Okay. We actually listed a lot of possible heterogeneous information. Like this arrow means this paper cite the other papers. That means if you cite this paper, whether you are going to co-author with him. Okay. So we took those candidate metapaths. We'll see which metapaths likely will play essential role. We have lots of data based on the past, right? Based on the past, we took this one as example, as candidates. We took a lot of data to test to see which metapaths will play essential role. Actually, we got a few, like we mark as a 4-star based on the p-value. The very sharp p-value means it has bigger prediction power. We look at the 4-star, we identify a few. You probably see these several 4-star ones actually quite interesting. This is a co-value, this is a co-author, this is a co-term. That means you share similar kind of terminologies. This is a co-citation. We found these 4-star paths, actually these several ones we found is pretty consistent with our own intuition. Okay. We use those metapaths, we do the prediction. The interesting thing is I took my own student, Jiawei, he got a PhD from me in 2002. We predicted from 2003 to 2009, okay, who will be his new co-authors. We identified the top 5. The interesting thing is, no matter you know them or not, whether they're a big name or not, we got this top 5. Actually, Riemann is sitting there. Okay. You probably see we got 5, 4 of them turn out to be true. Okay. The only one who is not true is Osman Diane. Actually, it was not a bad prediction because Osman was my student in the same group. Okay, we just predicted, they two graduated, they will collaborate. Okay. So I asked Jiawei, say, why you did not co-author with Osman? You were in the same group. Actually, to my own surprise, Jiawei said, not because I did not like it. Actually, your time frame is too short. We did have a co-author paper in 2011. Okay. So that shows, actually, the prediction was not bad. okay, even for the next several years. So with this power, you immediately will think, this is pretty powerful. Then we solve a problem, we can do lots of prediction, we can do lots of search, similarity search. What's the problem? Actually, the major problem is the real data does not really look like that. The real data is unstructured, okay? So you look at the majority of the real data, like newspapers, okay? They got lots of information, but it's hidden in the text, okay? So we got this 80% of data is not in the structured form. How can we dig out the knowledge? Okay. Our goal and our path is we are not just rely on the newspaper. We also rely on the word knowledge, like Wikipedia or something. But we don't want people to mark the newspaper explicitly. That means we don't want anybody to annotate the newspaper. We just want to use the general word knowledge that's sitting on the web. Okay. We integrate them. We want to do the phrase mining, typing, construct the structured networks, then we dig out knowledge. Then I'm going to show you what we are doing in that domain. That means we take the knowledge, we want to dig out the phrases. Okay. I'm going to first show you, we have several things we done in 2015. We just published those results, but we think it's critical to make progress to turn unstructured data into structured networks. Okay. So let's look at the first thing is phrase mining. Okay. Remember, the word may or may not be the integral, complete semantic unit. For example, I just give you a simple example. United. Okay. If I went to the airport, like in the US, I say United, nobody probably get confused. It's United in the other side. Okay. That means United Era. But if I go to United Nations, I say United. What do you mean? Okay. Actually, it's very ambiguous because United may be United States, United Kingdom, United Arab Emirates, or the United Nations. There could be many things united. That means if you use a single word, it's ambiguous. Okay. But if you put them as a phrase, say United States or United Kingdom, there's no ambiguity. Okay. So to that extent, we say we are trying to get into the text, we try to grab phrases instead of single words. Okay. But in the past, a lot of people are doing, say, annotation. But annotation is a human labor. We don't want to do human labor. Can we do it automatically? In the past, okay, there were people doing this using topic modeling. Okay. But the simple topic modeling just get single words, not phrases. Okay. Some people want to do phrase-based topic modeling. What they do is they first get a phrase, doing topic modeling, then within the same topic, they try to combine them into phrases. But that's too late. You think about this. Just give you a simple example. Okay. Knowledge discovery using least square support vector machine. If you do topic modeling first, you get knowledge and discovery separated. The support and vector separated. You will never be able to get knowledge discovery as a phrase, support vector machine as a phrase. Okay. So what we are doing is we change the order, we change the thinking. Okay. That means we first do frequent pattern mining. Okay. Then based on this to construct the phrases. We work out two algorithms. One is completely untrained. That means we do not use any word knowledge. Okay, we just go through the corpus. Okay. That one we develop an algorithm called topic mine. Okay, topic phrase mine. The second one is we do use word knowledge like Wikipedia. Okay. Then we develop a training-based method called set phrase. I'm going to show you, it's pretty interesting. These two frameworks work so nicely, we can dig out the phrase in a nice way. The first thing is the top mine. Okay, top mine means you do not use any training, you just based on the text data itself. It will say something important.
Why? I just give you a simple example. Okay, let's take this, as one title in DBLP called this Markov blanket feature selection for support vector machine. Okay. How do you know, Markov blanket is a phrase? Feature selection is a phrase. Support vector machine is a phrase. How do you know that? Okay. The interesting thing is you just read this one title, you have no way to figure out. However, we have 2 million, 2 point some million in DBLP. They are all different titles. You work it out, you're going to find it. How do you work it out? Okay, simple counting. You go down there, for example, you go down to this, there are many, many different titles. Okay. If you can find, just give you a simple example, support vector itself, how frequent support is, vector is. Okay. How frequent they get together. Okay. Actually, it's very easy. Anybody, you do the counting, you do the probability calculation, you will find their individual probability. If they combine together, okay, if they have no relation, they should just based on the independent distribution. You time them together. Okay. However, support vector, they do get together much more frequent. How frequent they are? If you use a standard deviation, okay, you can either say if they are 3 standard deviation away or more. Okay. That's not by chance. The chance is only 0.3%. They will get together. Okay. Now they do get together more than that. Okay. So you probably see if you are several standard deviation away, then the only explanation is they are friends. Okay. So we use this. We use similar, z-score things we call, these alpha tests or significant score tests. Okay. You probably can see support vector machine is really 12 standard deviation away. Okay. So they are phrase. Even they get together, they team up with machines, they are still several standard deviation away, they are phrase. That's why support vector machine is a phrase. The trick thing is here. Okay. If you look at selection, you get feature selection, selection for. Both are phrases. You think this. You do have a lot of selection for. However, if you check them, feature selection is tighter if you base on the standard. Once this one consumed by feature selection, the selection for in this particular one will not come. Okay? Because they're tighter group to group feature selection together, not selection for this one. Okay? So to that extent, based on phrase segmentation back into the text, you'll get feature selection as phrase, but not selection for. Okay. With this trick, plus we set up 4 other standards. These 4 standards are also very useful. You probably can see one thing we call popularity. That means if you think the phrase is a good one, they should be somewhat popular. Okay. The second one we call is concordance. That means they really get together in a nice way. For example, you see strong T, you never see powerful T. You see powerful computer, you never see strong computer. Even they are similar terms, you know which one likely to be a phrase. Like active learning is a phrase. But learning classification is not. Okay. Another interesting thing is informativeness. That means something getting together is like stop words, like this paper says. It's not a good phrase because it's almost anywhere you find this. Okay? And the completeness means if you find support vector, in the meantime you find support vector machine, they are very frequent, they share similar kind of frequency, especially for example for a vector machine. They share a very similar frequency as support vector machine. To that extent, support vector machine should be selected, not vector machine. Okay. This is really based on your corpus. For example, you really go to mechanical engineering or electrical engineering, you do find vector machines more frequent than support vector machine. Then vector machine become a phrase in that corpus, right? So with this idea, we actually can get lots of things done. I'll probably show you some examples, okay? I probably show sorry, I just think we got into the reverse. Okay. No. Sorry, just because, okay, I take this one in the reverse, direction and pick upside down. That's why when I click it, it all reversed. Okay. Let's look at some examples. This one has no training. This one is based on the Yelp review. You probably can see, for Yelp review, remember our system really from Mars. It has no knowledge about English. You probably can see this engrams, ice cream, iced tea, French toast, hash brown. This is like McDonald's. This is all like a fast food restaurant. Okay, give you the menu. The other one could be the second one actually is an Asian, restaurant menu. You probably see they are very nicely separated based on, you use phrase mining plus topic modeling. Okay. But more interesting thing is not only they got a quality phrase, but also very efficient, very fast. Just because you try to find frequent pairs, a simple counting is very fast. Then another question becomes, if I already have some knowledge, I give the knowledge as a training data. Can we do better? Okay, we developed another algorithm. This algorithm actually won the grand prize of 2015 Yelp Dataset Challenge. Okay. The one is we just put some word knowledge. For example, you only give a small number of labels by human, or you rely on some word knowledge like Wikipedia. Okay. So with this, we generate very high quality phrases. I probably can just show you. We took the DBRP data. One part is KDD, the other one like sigma or different things. You probably can see one line is what we generate. The other line is what the NLP people using the phrase. They basically they call chunking method to get it. Then you probably can see the red one is we found it, the chunking method, name chunker cannot find it. Like for example in KDD, we have time series, gene expression data, frequent subgraph, categorical attributes. These are pretty popularly used in data mining. Okay. However, they found something we could not find, or we do not worth to rank them high, like an important problem, effective way, or small set. This actually is not just for KDD, for anything, right? So to that extent, we generate very high quality phrases. The very surprising thing, even surprise ourselves, because we do not use language features. So you go down to other languages, you still can generate very high quality phrases for that language. We tried Chinese, which most of our students also can read because many of them from China, they can read those Chinese ones. We found actually generate pretty high quality Chinese phrases. We have one student who actually was born in Egypt. He actually generated Arabic phrases using Quran. Okay. Also generated pretty high quality Arabic phrases. And actually some other students tried Spanish, Japanese, Romanian. They all generate very high quality phrases. So this is very interesting, is we do not rely on language feature, just based on statistics. You have to use a bigger corpus. You just take one sentence you give me, I cannot do anything. But you give me the whole corpus, things become clear. But immediately you say, you got phrases, but can you, just based on phrase, construct networks? The answer is no. The reason is, you got a phrase, but you may not know the type of the phrase. If you do not know the type, you cannot construct a typed structured network. How can we get the type down? Okay. That's the one we just got this year's KDD conference paper. That one is really say, we got like a news, tweets, and Yelp, those kind of data. We want to automatically find types. Okay. But the previous one, like the people doing this in natural language processing is, they rely on human labeling. They took like 500 documents from New York Times 2013, they ask human to labor extensively on these 500 documents. If you really get a link, you need 20,000 queries. Okay? That's an NLP practice. We don't like that because how many people you give me a corpus, you need to spend the time to get 500 documents labeled. Okay? So what we want is that, just give you a simple example. Suppose you got a barbecue review, that said the best barbecue I've tasted in Phoenix. I had a pulled pork sandwich with coleslaw and baked bean for lunch. Suppose you got some kind of comments like this. Okay. But how, without human, intervene, the barbecue actually is food. It's not something weird or something like a machine who can cook barbecue. So there are lots of things you do not know. You try to put barbecue is food, Phoenix is a location. Actually, it's not that easy. Okay. Can we do this automatically? Okay. The interesting thing is, if we do not want human to intervene to do the manual labeling, we have to rely on some human knowledge. The people just came from Mars will not be able to understand this text anyway. Okay. So what we do is we took a Wikipedia, which more explicitly we took a freebase, which is something generated from Wikipedia, but they have structures. Okay. We take this as our implicit remote training data. Okay. Then we try to build links with the real text document. What are the problems if we rely on this? There are several major challenges. One challenge is that the thing may not be linked together. The first challenge is domain restriction. For example, you think the Wikipedia links everything, but you just give you a simple example, take Yelp reviews. Okay. There are lots of things you go back, even take the Yelp review, you go back, try to link with Wiki, you find it's not linkable. Many of them not linkable. Okay. Actually, we got statistics, only 7% in Northwest is linkable to Wikipedia, to the freebase. 93% not linkable. Then the second thing is their ambiguities. Just think example, Washington. What Washington means. In different contexts, Washington could be a state name, could be a city name, could be a person, could be US government. Okay. It could be anything. Okay. So to that extent, if we do not know, we blind link Washington to be a state just because the probabilities are high, then you make a great mistakes to understand the text. Okay. The third one is you want to build a bridge. The bridge is very hard to build. The reason is people say it in many, many different ways. Just give you a simple example. Look at this, several examples here. You probably see the tricks. The journalist just to say about Japan, the tsunami and nuclear accident, okay, just to look at the tsunami, you probably see the report said in many different ways. For example, you see this one says the magnitude 9.0 quake caused widespread devastation in the city. Okay, so you probably see for the same reason you can say ravage the city, ravage this area, or devastate this area. You can say so many different ways. Okay? So if you are not human, not trained, how could you understand this? How could you build links? Okay? So that's the trick. But the interesting thing is we have lots of data. Okay? You think about this. If you were, suppose, a journalist went to Afghanistan, was captured by Taliban. Okay. Suppose Taliban put you in the cell, give you only Arabic newspaper. Suppose you know nothing about Arabic. The first day you read it, it doesn't make any sense. Okay. But if they lock this journalist for a year, every day they give newspapers, things could be different. Because you got so many newspapers, if you're smart enough, you are going to build lots of correlation. Okay. Gradually, you may understand something. Okay. That's exactly what we did. Okay. That means if we take one sentence, one document, we cannot do anything. but you have hundreds, thousands of documents. You are going to build those graphs. Okay. The graph is that part, one part is just occurrence, mentioning. And you break them apart into different parts, you link them together based on their positions, you build this kind of graph. With this graph, you will be able to do clustering, to do propagation. Okay. The philosophy is you use this graph, you are going to do type propagation. You are going to do relation phrase clustering. That means you are going to take all the things you can link from your freebase, link them, and if you cannot link, you try to use other links to propagate them. Okay. How do you propagate them? You may need to do the relation phrase clustering. Okay. While you do better clustering, you do better links. You do better links, you can get a better clustering. Okay. You take turns to optimize them. Okay. So essentially, at the very beginning, you do phrase mining. And take the phrases, you try to construct these graphs, heterogeneous graphs. With graph, you are going to do the clustering, and you take them back and forth. Okay. So essentially, I'm not going to show you the detail, but I can show you some results which could be quite interesting. Okay. Just give you a simple example. How do you do the relation clustering? These are very different things. For example, this disperse, hit, struck, not. Okay. You think they are not related. But with the relation phrase, you gradually build, there are many such phrases, you will be able to link them together, cluster them together. Okay. So overall, it's optimization framework. If you study any optimization, this function, okay, was decomposed into several functions. And all these functions, one is doing type propagation, one is doing relation phrase clustering, one is do the mention modeling. These three get into the overall optimization framework. You just, everything is soft, but you can gradually, using something similar to EM, you will increase the score. I'll show you some experimental results, you probably will get convinced. Okay. The experimental results is we compete with the best set of NLP tools. Remember, a lot of NLP tools, they need human to do the training. You need to label 500 documents. We do not label them, we throw them to freebase. Okay. However, we take large set of New York Times, like Yelp data and Twist data. We'll show you, what's the power. Okay. This table probably can show you in a more interesting way this is New York Times data. Okay. New York Times data, you probably heard, you got a precision and recall, the final harmonic mean is F1. Okay. If you look at F1, the previous one, including the Stanford NER tool, you can see their F1 score, the highest one here, Apollo, is about 0.79. And we can get 0.93. Okay. And if you look at the year, you also see this is pretty high. The twist is a little more difficult. We're still trying to improve it at this point. But in KDD last year, we reported it's 0.45. It's still better than the others. It's not that high. But the interesting thing is you can do a lot of things, even compare with the best NLP tool. They do a lot of labeling. Okay. Just give you a simple example. This one is a Stanford NER, which is very popular used in natural language processing. Okay. For Stanford NER, they rely on labeling. We rely on distant learning, in the sense we only refer to the frequency. Okay. So you can see the Stanford NER got a F1 value of 6.68. We got 0.94. Okay. That's the same for Yelp. The similar thing is for Twist. Of course, Twist is more difficult for everyone. Okay. But the good news is you can see is we can link and correctly label many things. I just give you an example of this barbecue. Okay. Here you can see our method can identify barbecue as food, finish the location. Okay. The other ones. So what we developed is based on the recent paper published in 2015 is using relationship. Okay, you try to develop a using network embedding to do the relationship modeling. So, for example, we took lots of PubMed data, try to automatically develop a method to dig out relationship between gene and disease, drug and disease, drug and pathway, drug and target gene. Okay. The data we have is PubMed data. It's a medical publication. We randomly selected 10% of PubMed abstracts. That means we only get abstracts, the 10% from the PubMed. We actually developed these relation phrase embedding methods. Okay. That means we first do phrase mining. With phrase mining, we do the embedding, which is derived, the principle is derived from the recent deep learning. Okay. But the embedding is on the networks. It's not just on the similar neighbor keywords. Okay. Using this network embedding, I'll probably just show you some example with a limited time. Okay, let's show you this example. Okay. We took 10% PubMed abstracts. Okay. Then the interesting thing is you can give me one example. Okay. Suppose you give me one is breast cancer and BRCA1. Okay. Breast cancer is a disease. This BRCA1, or some people pronounce it BRCA1, is breast cancer gene. Okay, some kind of gene. You said this breast cancer actually is closely linked with BRCA1. Now I'm not going to study breast cancer. I just ask you, what about leukemia? What are the likely genes linked close to leukemia? Okay. The interesting thing is, with such massive data, with embedding, you're going to find these are interesting things linking to leukemia. Okay. And what about a gene? I give you a gene, like ALK. Okay. Say, what are the diseases related to this gene? You actually will find the problems here, like small cell lung cancer, non-small cell lung cancer. These actually link with this ALK gene. And you may give me, say, leukemia will link with this drug. Then you may say, what about the small cell cancer linked to what kind of drug? Or you give me this drug, say, aspirin. What are the problems linked with aspirin? Okay. So that's the result we dig out just based on the text data. Okay. Actually, we got very excited with those medical scientists and bioinformaticians because they look at this, they said, actually, what you discovered is quite true. Okay. So the interesting thing is we actually took a paper just published in August in Cell, this top journal, Cell 2015. Okay. This is Cell paper reported. This actually we use is our text mining using this embedding got it. Actually, if you look at the ranking here, it's not too far apart. It simply says they spend a lot of time doing lots of experiments to derive this. We actually spend no time on experiments. We only dig through this PubMed data using our computer in a very short time. We derive this, actually it's comparable with what they derived. That simply says, actually this network embedding and mining is pretty powerful. You can build up some relationship out of it. So I probably, it's really the time for me to give the conclusion. What I should say is network actually is everywhere. If you think about it, you are given a lot of networks like social networks or web. Actually, once you give massive text, you will be able to extract phrases, types, relationships. You're going to construct massive networks. And with these massive networks, you will be able to dig out lots of valuable knowledge which maybe spend years for other researchers to dig out, but you will be able to dig out from massive text. Why this is useful? Okay, some medical scientists actually challenging me said, then you don't need to do research. Actually, it's not. But other medical scientists, they found that this is very valuable. Why? They just give me a simple example. Said, PubMed every year, the incremental amount, the number of papers, the new papers add into PubMed every year now is over 1 million. Okay. Nobody in the world, no genius medical science in the world can read 1 million paper within a year. Okay. What they do, they say they rely on computer scientists, rely on network scientists. To build these networks, they are going to benefit out of it. That says we're not going to replace their research, but we're going to help. Okay. That's our general view. The network science, data mining, adding together could be very powerful. Okay. So that's my conclusion. We got lots of papers, but if you look at my book, we start from data mining to link mining, then the remaining ones, we get into the network, get into network mining. And these two newer ones actually were my student PhD thesis. Both of them received the KDD dissertation award, one in 2013, one in 2015. And they getting into the networks, getting into the text. I think that's a future for our network science and also future for computer science. So the work actually has been supported by lots of agencies, including Army Research Lab, including NIH and NSF. Okay. Thank you.
Thank you very much for this exciting talk. We have some time for questions, please. You have the mic behind you. Turn the mic.
Sir, you have been discussing the issue of extracting knowledge from the massive data. And one of the backgrounds, as I can see in your lecture, is that you are using data from some sources that may be considered as high quality data. If you just look at PubMed information sources, then it is obvious that these papers were reviewed, peer-reviewed, and so on, so that the information contained there is accurate, and if you extract something from this, then you will have some valid information. But did you ever consider extracting knowledge from such, say, noisy sources like, say, web, where you actually do not know whether or not these documents that you are processing really make sense? Is it at all possible to extract knowledge from such noisy sources?
Yeah, that's a very good question. The question is, the document itself could be noisy or could even be wrong once you extract them. Okay, of course, there are concerns on this. You probably can see, we take the, take PubMed data. Most of these research publications got some review. Okay, doesn't mean they're all right, but they are of reasonable quality from their own scientists. Okay. And even that, they may contain different claims. For example, things published 20 years ago and now could be completely conflicting. Okay. So actually, I have a research group in my team. Essentially, they are doing, they call claim mining and truth finding. Okay. Essentially, it's trying to mine the research paper, finding their claims. Okay. But you get one paper, get some claim, but there are hundreds of other papers that may get different claims. They may get conflicting ones. Okay. From those conflicting claims, we're going to mine likely which one to be the right one. Okay. That one we call truth mining or truth finding. Okay. You may think it's pretty risky or it's pretty puzzling. you got lots of conflict things. How could you find which one is true? Okay. Actually, there are a lot of statistics. We have some studies. You link them into another kind of networks. Okay. You based on, one thing could be based on consensus. Most people claim this one is right, likely could be right. Another is based on the authority of information providers. That means who may provide better quality information. Actually, these two are mutually enhancing each other. We put them into a loop, into an iterative process to try to find authoritative, claims and try to find the consensus. And these two things actually, iteratively, you're going to find the real truth. Okay? Of course, you still cannot guarantee 100% is right, but we did some good experiments, like finding authors of the papers and finding directors of the venues. Actually, there are noises, but once you get many sources, integrate them together, you will be able to find the real truth. The chance to find the real truth is very high. Okay.
Thank you. Anything else? I have one short question about following also the previous one a bit, about the provenance and about the evolution of the language, because also new words appear, new phrases appear, also coming from other languages, depending even on the event. So you have in Charlie Hebdo, we have the terrorist attack, and it is a French phrase which suddenly appeared in the English language. So it's something new, while the other phrases change their meaning. Of course, it is not the fast the process, but it exists also. So one question is about time, and another about the provenance and usage of this provenance, while not only in terms of the credibility, but also the meaning of the certain phrases or the syntax and so on.
Yeah. That's also very good observation. Actually, the claim, even try to go into the text to find the right claims, actually is pretty challenging. We have two lines of thing. One line is already structured. For example, the paper authors or book authors or movie directors, they're already structured, but they contain the conflicting information. That means you said this book was authored by ABC, the other one said it by BCD or something. Who is right? Okay. So that's the one based on structured data. But the other one is mining claims, which actually is more challenging in the sense you got the text, what exactly they're asserting in the text as a final conclusion or claim. That one actually is we currently are doing and not got a paper published. Is still involved. You dig out the types, and then you actually try to verify based on many papers, not based on one paper. Some paper you already know the claims. You try to propagate this in a similar way to get at the other paper, also try to find claims. Okay. But there are lots of research problems. You probably can see. Within this framework, there are many research problems. Just give you a simple example. We mined the language. Actually, we got one email from TripAdvisor because all of these several papers are open source. We actually put into the GitHub, anybody can use it. TripAdvisor, they actually using it, they mine it, they got very excited with the software. Then they say they actually want us to see the tricks on mining different languages, because different languages still need to input some different subtlety inside. They actually give us a task whether we can work with them together. Also mine like French, Russian, or many other languages. We are discussing with them. I think it's quite interesting to see for different languages they have. For example, mining Chinese language, you have to first use some kind of Chinese. The initial phrase identified, because the Chinese, they even do not have gaps within every word. There is no gap. It's not like there is a space between two words in European languages. So it's much more difficult. We actually use their pre-processing, then we do the phrase mining.
So thank you once again very much.
Okay, thank you.